What's up everyone, and welcome back to another episode of Stelzer's Science. I'm Mr. Stelzer, your future best friend or worst nightmare in AP Chemistry. Today we are going to be covering the Unit 3 exam review. Let's get started. Alright, so heading over to the review. Let's move this way. Let's full screen it. Let's pick a color. I'm thinking like a blue today. Alright, ready to go. So 14 questions in 21 minutes. We know the drill. We've done one of these before at this point. Let's get to it. So question 1. The figure above shows that in solid hydrogen fluoride there are two different distances between the H atoms and the F atoms. Which of the following best accounts for the distance differences? So one is B. The reason that these two are different differences, one is 100 picometers, one is 150 picometers, is because one is a covalent bond and one is an IMF. And we have this relation that the stronger a bond, the smaller it is. So covalent bonds are stronger than intermolecular forces. The covalent bond should be smaller than the intermolecular force due to that relation. Question 2. If 50 milliliters of 1.0 molar sodium hydroxide is diluted with distilled water to a volume of 2 liters, the concentration of the resulting solution is. So this is M1V1 equals M2V2. And just the typical dilution equation, we're diluting the equation, use this one. It's not given to you on your equation sheet, but it's not a hard one to memorize. The initial molarity is 1, the initial volume is 50 milliliters. We want to know what the final molarity is, and the final volume is 2 liters. Now that is in liters, not milliliters. The units do not match. It does not matter whether you use milliliters or liters for the dilution equation. However, it needs to be consistent on both sides. The same goes with like combined gas law, for example. So that would be 2,000 milliliters. So 1 times 50, which is just 50, divided by 2,000 is 0.025 molar. Answer is A. We have a Maxwell-Boltzmann distribution curve of molecular speeds in a sample of two different gases at the same temperature as shown below. So right away, at the same temperature sticks out to me. Both of these gases have the same average kinetic energy. So kinetic energy is the same. You need to make sure that when it's saying that it's at the same temperature, you recognize that it's the same kinetic energy. Which could mean the same speed if we're looking at just the same sample of gas. But we're comparing two different samples of gas. Which gas has the greater molar mass? Kinetic energy is equal to 1/2 mass times velocity squared. We're looking for the greater molar mass. The one with the greater molar mass is going to be the one with the smaller velocity, since kinetic energy has to be the same. So the one with the smaller speed is A. A is further to the left on this graph, so A has to have the bigger molar mass. So first 3 done. Got to double check just to make sure I got all of them correct, and we're good. BAA. Right, 4, it looks like we have a piston here going compressing, so we are lowering the volume. A sample of C4H10 is placed in a rigid vessel with a movable piston. The volume of the gas is reduced by moving the piston downward while the temperature is maintained at 25 degrees Celsius. So we are not changing temperature. As shown above, the pressure of the gas versus its volume is plotted in the graphs below. Which of the following best explains the increase in pressure when the volume is decreased from 0.5 liters to 0.05 liters? So we have a graph of pressure versus volume, not pressure versus time. This is not showing how pressure changes versus time. All we're saying is that when the volume lowers, when we lower that piston volume, when we move to the left, that pressure goes up. So why is that? It's because the molecules are striking the vessel more frequently. A. They're not striking the vessel with a greater force. C is a tempting one to choose, but since the temperature is the same, that means the kinetic energy is the same. So they're not hitting the walls any harder, they're just hitting the walls more frequently since the volume is way smaller. 5. Which of the substances listed has the highest boiling point and why? We have neon, hydrogen fluorine, C2H6, and methane, CH4. The answer is going to be the HF because it experiences hydrogen bonding, while the rest do not. The rest are nonpolar. HF has the strongest intermolecular forces, so it's going to have the highest boiling point. So for this page, it was A and B, and then we got A and B on the answer key. At room temperature, I2 is a molecular solid. Which of the following provides a characteristic of I2 with a correct explanation? It has a high melting point because it has weak intermolecular forces. That one just doesn't check out. High melting point would mean strong intermolecular forces. It is hard because it forms a three-dimensional covalent network. That one's not true. I does not form a covalent network. Also, we're told it's a molecular solid. C is not a good conductor of electricity because its valence electrons are localized in bonding and non-bonding pairs. That one looks correct. Let's read D first. D says it is very soluble in water because the molecules are polar. I2 is nonpolar. So the answer is C, just by process of elimination. C is the only one that could be true because the other three are definitely not true. And C is true. I2, when it's in solid form, does not have moving electrons. It's not a metal. Only metals have those moving electrons. Ionic compounds don't have that. Molecular compounds don't have that. They need to be dissolved in order to conduct electricity. 7. The diagram above shows a thin layer chromatogram of a mixture of polar products from a chemical reaction. So we're doing chromatography here. That was a big word. I'm just going to ignore that word. Chromatogram. We have chromatography. So the separation was performed using 50% ethyl acetate in hexane as the solvent. So the solvent is ethyl acetate and hexane together. And silica gel as the polar stationary phase. So usually we don't really care about the stationary phase, that's just what it's traveling up. On the basis of the chromatogram and the information about solvents in the table above, which of the following would be the best way to decrease the distance that the polar products travel up the plate? So we're given that the product, it's almost a throwaway line, but that's actually really important. The product is very polar. So chromatography's experience is very complicated. However, what we're looking for is the mobile phase, is what's traveling up the paper, polar or nonpolar, and it is the solvent front, polar or nonpolar. So we're given that these two are polar. So in order to decrease the distance they go up the plane, we want our solvent to be nonpolar, which means it would mean more hexane and less ethyl acetate, because ethyl acetate is polar and hexane is nonpolar. So use pentane instead of hexane. That wouldn't change anything. Decrease the percentage of ethyl acetate. That looks like the answer there. Increase the percentage of ethyl acetate. That doesn't make sense because that would increase the distance the product travels up, because we have a more polar solvent carrying up a polar mobile phase. Add 5% methanol to the solvent. No, we don't want to do that. Methanol also looks pretty polar. That would increase the distance. So that was a lot there. The answer is B. So for this third page, it's C and B. Good. All right, use the following information for questions 8 through 10. A student uses visible spectrophotometry to determine the concentration of cobalt-2 chloride in a sample solution. The first student prepares a set of cobalt-2 chloride solutions of known concentration. Then the student uses a spectrophotometer to determine the absorbance of each of the standard solutions at a wavelength of 510 nanometers and constructs a standard curve. Finally, the student determines the absorbance of the sample of unknown concentration. We did this experiment. We literally just got done doing this experiment, but instead of cobalt 2 chloride, we used copper. We used copper 2 sulfate. We pick a wavelength, then we check absorbances on known concentrations, and then we make a plot, and then we test our unknown concentration and see where it falls on the plot. So, classic spectrophotometry experiment. A wavelength of 510 nanometers corresponds to an approximate frequency of 6 times 10 to the 14th. What is the approximate energy of one photon of this light? Okay, well, they give us the frequency. Energy is equal to Planck's constant times frequency. So energy would be equal to 6.626 times 10 to the negative 34th times the frequency, which is 6 times 10 to the negative 14th. Plug that in your calculator. 6.626 times 10 to the negative 34th times 6 times 10 to the 14th. I don't know why I wrote negative 14th. It's just 14th. And we get 3.97 times 10 to the negative 19th, which is like 4 times 10 to the negative 19th, D. A student made the standard curve above. Which of the following most likely caused the error in the point that the student plotted? All right, back up to this question. Just whenever you see like photon of light, energy, wavelength, frequency, go to the equation sheet, use those two equations. We only needed one of them, but we could have done this equation if they only gave us this wavelength. So it was just plugging into this equation. All right, back to 9. We make this curve. What caused the error in that point? So this point right here, this point right here is the outlier point. So every other point falls on our line. That point looks like an outlier. That point, its absorption is too low for the concentration. The point should be up here. It should be moved up. So what that lets us know is that for this concentration, we have too low of an absorbance. So that's either one of two things. So something is causing the absorbance to be lower than what we expect. A, there is distilled water in the cuvette when the student put the standard solution in it. I think that could work. Like if we had distilled water in there, that means we accidentally diluted it a little bit too much, and the absorption would be less than what we expect. There were a few drops of the 0.1 molar cobalt-2 ion standard solution in the cuvette when the student puts that solution in. That wouldn't make sense. That means our absorption would be higher than what we would expect because we're concentrating it. We would be accidentally adding too high of a concentration in there. So not B. The student used a cuvette with a longer path length than the cuvette used for the other standard solution. That would also increase the absorbance. If we had a longer path, if the light had to travel through more cuvette, the absorbance goes up because it has more, the light just has to make it through more stuff, so more of that light is getting absorbed. The student did not run a blank between 0.05 solution and the one before it. That just doesn't quite make sense. Really, we run a blank at the beginning. So the answer there is A. The original solution used to make the solutions for the standard curve was prepared by dissolving 2.6 grams of cobalt-2 chloride in enough water to make 100 milliliter solution. What is the molar concentration of the solution? So this is just molarity. Molarity equals moles over liters. We need to get to moles. We have 2.60 grams. It's 130 grams per mole. So 2.6 divided by 130 is 0.02 moles of the cobalt-2 chloride. And so plugging back into this one, molarity equals 0.02 moles over liters. It's in milliliters, so convert to liters. It's going to be 0.1. Move the decimal point over 3. So 0.02 divided by 0.1 is 0.2 molar solution, which is A. Let us check our answers. We have D for 8, we have A for 9, and we have A for 10. We're doing good. All right, last 2 pages. A student places a piece of iodine I2 in 50 milliliters of water. Another piece of I2 of the same mass in 50 milliliters of C6H14 and shakes the mixtures. The results are shown above. What do the results indicate about the intermolecular interactions of the substances? This one looks like we're doing like dissolves like. So this I2 was put into water and put into this C6H14, which looks really, really nonpolar. I2 dissolved in the C6H14, but didn't dissolve in the water, because I2 is also nonpolar. Like dissolves like. Nonpolar solutes will dissolve in nonpolar solvents. So I2 and C6H14 have similar intermolecular interactions, while I2 and H2O do not. The answer is B. The diagram above represents 2 samples of xenon gas in containers of equal volume at 280 Kelvin. Which of the following correctly compares the 2 samples in terms of their deviation from ideal behavior, and why? Both are the same gas, same size containers. It looks like sample 2 is going to deviate more from ideal behavior because we're going to get more particle-particle interaction. And we do not want particle-particle interaction for ideal behavior. We want those particles to not interact, to not run into each other, to not form potential intermolecular forces with each other. We just want them to bounce into the walls. So the gas from sample 2 will deviate more from ideal behavior because the xenon atoms are closer together, leading to an increase in intermolecular attractions. B looks correct. C says sample 2 will deviate more because the average speed is less, but both are at 280 Kelvin, so both will be at the same speed since they're both xenon gas. So another instance of they're telling you temperature is constant, and you have to make the connection that that means that kinetic energy, and in this instance, speed is constant as well because it's the same gas, so they have the same mass. Which of the following processes are covalent bonds broken? The answer for this one is D. C is ionic, not covalent, so it's not C. B and A both look like IMFs are broken, not the actual covalent bonds themselves, because it's just a state change. State changes are intermolecular forces. D is a covalent network. Covalent networks are held together by covalent bonds. So when this diamond turns into carbon gas, we are physically breaking apart those carbons from one another. 14. The survival of aquatic organisms depends on small amounts of oxygen gas that dissolve in water. The diagrams above represent the possible models to explain this phenomenon. Which diagram provides the better particle representation for the solubility of oxygen gas in H2O? So this one looks a little bit complicated. What's happening here? So we have an oxygen gas surrounded by waters, and we're asked, how does the oxygen gas behave with the water? Oxygen gas is nonpolar, which means it can only form London dispersion forces. A London dispersion force is a temporary dipole. So it's not going to do whatever's happening in diagram 1. This looks like more like a hydrogen bond, but O2 can't hydrogen bond. Instead, diagram 2 looks more correct. It's trying to represent a dipole. It's trying to represent a negative end and a positive end for this oxygen molecule, and the oxygens are attracted to the positive end. The hydrogens are attracted to the negative end, just like we would normally draw waters around like a positive ion or a negative ion. This looks like a London dispersion force. So it's diagram 2. Because the polar H2O molecules can induce temporary dipoles on the electron clouds of the O2 molecules. The answer there is C. D says diagram 2 because the nonpolar O2 molecules can induce temporary dipoles on the electron clouds of the H2O molecules. That's backwards. The H2O molecules, they don't need temporary dipoles. They have permanent dipoles. They have dipole-dipole. It's the oxygen gas that needs to be induced into a dipole because it normally doesn't carry a dipole because it's nonpolar. And that's what a London dispersion force is. So let's check the last 2 pages. We had B, and then we had D and C. All right, 14 for 14. I didn't fumble on this one. Look at them go. All right, that is it for the multiple choice. I'll go ahead and post this one, and then I will do the FRQ momentarily. All right, I need to exit. All right, see you in the next one.